Hello everybody, my name is Thorsten Höffler. I'm a professor at ETH Zurich, and now I'm presenting here the HammingMesh talk that I presented in 2022 at the Supercomputing conference in Dallas, Texas. Many people requested that I record this talk separately, so I'll finally get to it. This is a very interesting topology, a network topology for deep learning that I developed with many colleagues, as you can see here, while being on a sabbatical at Microsoft, where we did many other exciting things that I can't talk about that openly here. But here, about half the authors are from Microsoft, about the other half are from the group at ETH Zurich. So it's a nice collaboration to get all the results at the end. To just be very precise in crediting the structure of the topology and all the base was derived while at Microsoft. The experiments and essentially all the analysis with the different workloads that I'm going to present was performed at ETH Zurich. So, but let me get a little bit more to the motivation here. So why do we even care about specific network topologies for deep learning? Well, because deep learning is now, especially in the supercomputing field, one of the most important workloads. So big companies, social networking companies like Facebook now build supercomputers. Tesla, a car company, builds supercomputers. Google, a company known for its advertisement as well as organization of knowledge, they built very large-scale supercomputers. And Microsoft, a software company in many ways, it's now in transitioning or has been transitioned to a cloud data center provider with Azure, is also building very large supercomputers in a collaboration with OpenAI. Fortunately, that was founded while I was there. So here, there are even comics on Microsoft. So here, 10,000 GPUs. Just last month, we heard that the newest system is more than 14,400 GPUs, now listed as top 3 on the top 500 list. So companies, private industry gets very serious about building very large supercomputers. Why is that? Well, it is because of deep learning. So deep learning is a very interesting workload where you literally train a model to predict the sentence or the distribution of text on the internet. And how do you do this? And I'll explain in a minute why you do this. So here you take text from the internet, like this text, you remove a word, you run it through a function that has many millions or even billions of parameterizable elements, so-called parameters, and then the function gives you a prediction, a statistical model of what it could be, what is the likelihood for each of those words removed. So it tries to guess the removed word, essentially. Here you see with a 70% probability. It's not, but of course you know what the word was that you removed from the text because you removed it, so you can just remember it. What you do then is you update these weights, these parameters that I just mentioned, in the backward pass using very simple backpropagation methods iteratively over and over again, such that the model, when asked again about a removed word, will predict the right word. So why do we care about the statistical language prediction at very large scale? So hundreds of billions of parameters, as we will see in a second. Well, basically all of human knowledge is somewhere on the internet. The internet is an extremely rich corpus of text generated by humans. What I'm talking about now will be for sure transcribed to a written representation and will for sure go through many of these language models that they will learn, just like you learn from what I'm talking about right now, that learn from my spoken text. So this is just fascinating. So hundreds or tens of millions of hours of text we have at our disposal. And the language model can read much more than a human can read in a lifetime and represent this rather inefficient, but still possible, statistical distribution. So now, how do we get to the human scale? So how do we get the language model to be really good? Well, we train it with a lot of tokens. So many more tokens that a single human can read in his or her lifetime. So in GPT-3, for example, 500 billion tokens. Today, many more. And soon the whole internet, actually. Furthermore, the model itself is extremely large. It has the GPT-3 model, which is one of the older, smaller models, has 175 billion parameters. People don't even talk about the size of the modern models like Gemini or related models anymore. It's all speculation, or even GPT-4 is a speculation. So that's interesting. These parameters are 700 gigabyte in FP32. So I would expect that we have multiple terabyte-sized models today in operation. And the output is then basically language. So tokens. 30 to 50,000 tokens are in a dictionary today, in the English language dictionary, and of course different languages require different tokenizations, and it requires weeks to train such a model. So this is really a classical supercomputing task. This is quite nice. So, but now let's go a little bit more into detail, because these models are so large, we need to train them on a distributed system. This is why we are at supercomputing. Here we know how to build distributed systems for parallel performance, very large scale systems, namely the largest on the planet as represented by the top 500 list. So the simplest form of distributing a model is so-called data parallelism, where we take the elements of a batch. And now what is a batch? Well, it's actually call it a mini batch. A mini batch is a set of text, so pages of text in some sense, that you're feeding through the model for a single gradient update. So for a single update of the weights. Like I told you on the previous slide, there was just a single sentence with a single removed word, but we are actually using multiple sentences with many removed words at the same time, and we call this a mini batch. Now, the whole internet is cut into multiple mini batches, like we are seeing here. It's not four, it's in reality it's more like 4,000 or 40,000. But each of those mini batches is then cut into smaller pieces, like we can see 3 pieces here, that go through different copies of the full model. So we break the mini batch into pieces, we run them through different copies of the model, but then before we apply the update to the weights, we average them across all the pieces, such that for the next mini batch, we have a consistent view, and all of these 3 different model copies here are actually the same weights. So I hope that makes sense. This is really what the all reduce operation in data parallelism is doing, to averaging the weights. But now I mentioned each of those models has 700 gigabyte of parameters. Well, I don't have an accelerator with 700 gigabyte of memory. So what I need, so I cannot copy this model to my accelerator, because each of the accelerators here, like the green, the blue, and the brown one, would need to hold the full model state, which is impossible. So what do I do then? Well, I cut the model layer-wise. So each of these models has multiple layers. So for example, GPT-3 has 96 layers. So I can cut it into 96 small pieces and process each piece on a different accelerator. Great. Then I have solved the memory problem. But then you may actually have distributed the model, but you may want a faster solution, because if I process each piece on a different accelerator, I will actually get slower than I was before, because now for each model I still need to go, for each forward pass I still need to go through all the accelerators, but it'll just add communication time. So I have enabled larger models with pipeline parallelism, but I have in fact slowed down my computation. How do I make the computation faster? Well, I do this with operator parallelism. What do I do? Now each layer itself, you can call this an operator, but actually a layer consists of multiple operators, but call it a macro operator or combined operator if you like. But each layer itself you can cut into multiple pieces now. For example, in the Megatron paper, that's where people discuss this in great detail, how to actually split a transformer encoder or decoder block elegantly across multiple accelerators. So now what we can do is we can put all of these 3 pieces together, data parallelism, operator parallelism, as well as pipeline parallelism, into a 3-dimensional scheme. So, and now this scheme is quite an interesting one. By the way, this is well known since quite a long time. So we wrote a paper about this in 2018, where we first established this 3D parallelism at its full glory, collecting it from a large number of different research papers, where we first bring this together into one coherent scheme. So now, if you look at this from a communication perspective, data parallelism, pipeline parallelism, and operator parallelism, they have very similar communication patterns. So actually, data parallelism, as I mentioned, is really an all-reduced communication of rather large data, of my whole weights in my model. So now, what would I do? I typically don't have too many model copies in this dimension, because every model copy wastes a lot of memory in some sense, because I have duplicate parameters, but it's still a useful model to do. So I'm running a very large reduction on a relatively small communicator in MPI terms. The best algorithm, or one of the best algorithms for this, is actually a ring communication algorithm. So you communicate with each of your neighbors. The pipeline parallelism itself is naturally a communication with each neighbor, because every pipeline stage produces the activations, and it's sending it to the next pipeline stage for consumption. Itself, the producing is probably receiving it from some input. So it's also a nearest neighbor communication, but in a different dimension. You can see here the data parallelism dimension, we have multiple copies of the model and have a ring among those copies. In pipeline parallelism, we take each of those copies and now have a path from the input to the output and back in the backward propagation path. Operator parallelism in these large language models, so specifically Megatron, is also a somewhat nearest neighbor communication, but in a third dimension now. In each of the operators, we are now splitting here in the vertical dimension into their pieces, which are processed in parallel, but we would also be doing an all reduce or a broadcast or an all gather operation. All of these three operations at this scale you would represent very likely by ring-like algorithms, or you can represent by ring algorithms depending on your topology. And now if we put this all together, what are we seeing? We are actually seeing a three-dimensional torus structure. If we split the model into full three-dimensional parallelism, data, pipeline, and operator parallelism, the overall communication pattern is the three-dimensional torus structure. So this is quite nice, actually, because now can we take advantage of this? Well, this is now the question. First of all, do we need to take advantage of this? And it turns out that the network bandwidth is extremely important in AI supercomputing. So memory bandwidth I can satisfy locally with HBM, newest devices giving us a 3 or more terabyte per second memory bandwidth. This is just amazing. And then there's a lot of research in this area, like SK Hynix built the first HBM DRAM for NVIDIA that you can now buy in the Hopper product line of NVIDIA, also Grace Hopper product line in the Hopper piece. So, but what about the network bandwidth? Well, the network bandwidth is actually much more complicated because it's relatively low. So you have local memory bandwidth of 3 terabyte per second, but in today's HPC networks, you have 200 gigabit per second, which is 25 gigabyte per second. So that is quite low. Well, InfiniBand gets you to twice that, 400 gigabyte per second. But actually, if you're looking on AI systems, 2-year-old AI systems, like the Google TPU V2, specifically built for AI acceleration, that has 1 terabit per second. So 5 times as much as Slingshot today. AWS Trainium has 1.6 terabit per second network links. The DGX2 with lots of A100s has 4.8 terabit per accelerator. And much of this goes into NVLink, but this is just the connectivity that the chip has. Actually, Tesla's Dojo was announced at 128 terabit per second. Since then, they dialed it back. But just as a comparison point, a Broadcom switch or an NVIDIA switch with 64 ports at the time had 51.2 terabit per second. So the AI accelerator has more bandwidth than a network switch is actually built to push bandwidth. So that's quite an amazing feature. And the reason is because these DAGs that we have to cut, like I showed in the previous slides, they have rather big cuts and require extremely high bandwidth, especially along the operator parallel dimension. So we see a discrepancy of about 640 times between what we employ in the exascale systems today, many of those Slingshot based, if not all of those, and the planned Tesla Dojo system that was originally designed for 128 terabit per second for pure AI learning workloads. So somehow our AI systems, they may get entangled in cables at the end to deliver that very high bandwidth. But now, could we just take our normal topologies, many of the systems we have of fat trees, and build such a network with a lot of bandwidth? Well, we can. Actually, building a fat tree with 16,000 endpoints and 1.6 terabit bandwidth, like the AWS Trainium, and full bandwidth and 1.6 terabit, would cost $680 million. So it's maybe not the best idea to spend that much money, because conventional HPC topologies are unaffordable at the required bandwidth for artificial intelligence networks. So what do we now do? Well, why don't we take advantage of the three-dimensional parallelism fact that it's a three-dimensional torus and build truly co-design an AI supercomputer with unprecedented high local bandwidth, but also cheap global bandwidth. And this is what we did. So we looked at an accelerator package. You could now say, well, an accelerator package is a natural two-dimensional structure. Right? So it's on a board. These chips are naturally two-dimensional. They have many metal layers, yes, but it's an O of 1, so a limited number of these metal layers. And now you attach into the 4 natural dimensions of the four natural directions in a two-dimensional package, you attach north, east, south, and west links. Let's say these are 400G links. So you put a little switch in there that now switches 4x4 only. So it's extremely cheap because it's a very, very small switch with very simplified logic. It's part of your accelerator. And it's a normal packet switch like you would be building a bigger one with, but it's a 4x4 switch. And then you put many of these links, in this case 4 times 400G, so 1.6 terabit per second would be a possibility. Then you take many of these accelerators and stamp them on a bigger board, because these boards are actually PCB boards, so they have the dotted connections here are relatively cheap, and then from each board you have external connections. Now you need to somehow link these external connections, but what you can now do is you can arrange these 2D boards again in a two-dimensional structure. So we have 4 chips on one board here, and now we arrange many boards, actually x times y many boards in this view graph here. And now what we do is we do not just connect them with the nearest neighbor, because that would limit the flexibility a lot. If we would just connect them with the nearest neighbor, we would get a two-dimensional torus like Google has built in their first version of their TPU scale-out network. But what we are building here is we are fully connecting each plane, right? Each x dimension, and we are fully connecting each y dimension with standard switches. And this is the crux of the HammingMesh topology. So at the board level, it's a mesh, right? It's not a torus, it's a mesh. But at the system level, it's fully connected with switches as a fully connected graph. And this is, as you can see, many of you are mathematicians, you can immediately see this is a Hamming graph. This is why it's called HammingMesh. So by the way, later, Google used a very similar topology, simply with optical routing, for their newest TPU line. But that was later, after we talked about this here. So there may be a trace of inspiration. Who knows? But it's essentially an equivalent topology. They don't use packet switches at the top level, but they use optical circuit switches. And they do it 3-dimensional, but it's trivial to extend this from 2 dimensions to 3 dimensions here. But why do we do it this way? Or why would you do it this way? Because you can build rather big boards, like your 4x4 board. And you see all these onboard connections. They're very cheap because they're just PCB traces. They're extremely short if you can integrate your system, and extremely cheap. So you have a 2D substrate where you essentially only pay for the off-board connectivity. And that is, you have n square O of n square cables within the board, but only 4 times n off-board cables. So this is very important. So bigger boards is better. But of course, bigger boards, the biggest board would be a 2D torus, so that's not good because it limits your flexibility. It's all the trade-off between the board size and now the cost of the system. Because a 1x1 board would basically be a fully connected fat tree, right? So you can now adjust these things back and forth. So each board, each element has 4 dimensions. We have 4 planes per accelerator in this example. We have A times B accelerators per board. And these links are virtually free that are on the board because these are PCB links. So now this is a very interesting bandwidth flexibility trade-off, because now the global fat tree has, of course, the highest flexibility and the highest bandwidth. You can literally map anywhere and you always get full bandwidth. If it's a fully configured bandwidth. A local topology, for example, a 2-dimensional torus, has the lowest global bandwidth, but also the lowest flexibility. And HammingMesh is somewhere in between. As I mentioned, one extreme configuration, if I have 1x1 boards, is a fat tree, or is equivalent to a fat tree. And another extreme dimension, if I have no global links, if I have just boards that are essentially the size of your system, so there's no switch involved, I have a 2D torus. So HammingMesh is somewhere in between those 2 extremes. You can easily generalize this to 3-dimensional, 4-dimensional torus base configurations or mesh-based configurations, so no problem at all. So now, interestingly, for ring-based communication schemes, all of those networks are equivalent in terms of global reduced bandwidth. Nice. That is very nice, because you can always map these rings if you run a full system job. But now, the global bandwidth, if you're communicating randomly or if you're running many smaller jobs that want to communicate, is unfortunately very low for the 2D torus, and of course extremely high for the fat tree. And the HammingMesh, it depends on the configuration. It can be better, it can be worse. The placement flexibility, where do you put jobs, is extremely limited on a 2D torus. If I have a job which is very far, where the nodes are very far apart on the torus, it's an extremely bad configuration. So I need to pack jobs to get a full bandwidth. It's very hard to do this, as you can see in many papers by Argonne National Lab about how to pack jobs into the 3-dimensional torus of the good old blue gene architecture. On a global topology like a fat tree, it doesn't matter. It's completely vertex transitive, so it doesn't actually, you can't even tell the difference where you map these things. There are some differences, but that's mainly the routing, the limitations of the routing. In a HammingMesh, well, again, depending on the configuration, and we'll actually show later that it's extremely flexible, I can map those very flexibly to the system topology. And then the cost per injection bandwidth is now where HammingMesh shines. Because due to these PCB cables, it can be extremely cheap depending on your base topology. It's as cheap as a fully customized 2D torus. In this case, we're looking at 2D torus. It's not fully customized, but you could do this. But it's much, much cheaper than a fat tree topology. Okay, so now some basics of the HammingMesh topology. Well, you have always what we call an HXA mesh, is an A by A board arranged in an X by X configuration, like X by X boards, but each of those has A by A many accelerators. So we always use square things because it's easier to reason about it. You could make it A by B and X by Y if you want to. The relative bisection bandwidth of an HX2 mesh, so 2 by 2 boards, is 25%, and HX4 mesh is 12.5%. So it's relatively low. A fat tree has 100%, but it comes with a cost benefit. The diameter is kind of simple. HX2 mesh is 4, HX4 mesh is 8. You get the equation for arbitrary ace there. And we have a certain cost model here where we just looked up prices for switches and AOC cables and DAC cables. So difference between AOC and DAC cables is really the AOC cable is rather long, adaptive optical cables, and DAC cables is direct attached copper. These are electrical cables. They're rather short. So you have to be careful here with the price, of course. And we're looking at two topologies, one 1000 endpoint topology with HX2 meshes, where we have 16 times 16 many boards of those. In the HX4 mesh, we have 8 by 8 boards. We're looking at a large topology where we have 16,000 endpoints. With 2 by 2 boards, we need 64 times 64 many to fill 16,000 endpoints approximately. And within HX4 mesh, of course, we have half of those. And we assume that there is, in this case, there is one switch per plane, because we can buy 64 port switches, which is quite nice, as you will see. So this one gets quite cheap. Because we only have one switch in each plane. We don't need a fat tree in each plane. It's also possible to do this, but this is just makes it more expensive. So if we now look at the 16,000 accelerator case, we look at the cost of various topologies. So we have a non-blocking fat tree. Here we have a 50% tapered fat tree or 75% tapered fat tree. We have a Dragonfly, a 2D HyperX, an HX2 mesh, an HX4 mesh, as well as a torus. You can see the cost of the non-blocking fat tree is just not negotiably high, $680 million. The 75% tapered is still $270 million. It's cheaper than the Dragonfly, but of course it has a much lower bandwidth. HyperX is at $400 million, HX2 $200 million, HX4 is only $43 million, about the same price as a torus network in our estimate. Now comes, of course, the global bandwidth in percent of injection. The non-blocking fat tree gets nearly 100%. The tapered fat trees, as expected, about 50 and about 25%. Dragonfly at 71%. The 2D HyperX gets 95%, significantly cheaper per global bandwidth, so it's a nice topology. By the way, the 2D HyperX is also a variant of a HammingMesh. So it's actually a 1x1 HammingMesh. So if you look at it in detail, so that's kind of a special case, but we still model it separately. And then we have the HX2 mesh and the HX4 mesh running at 25% and 10%. And the 2D torus is at 1% of the global bandwidth, very, very poor. And these are all simulation results. Now we can compute the relative cost savings over the fat tree for global bandwidth. So of course the fat tree is 1x cost per global bandwidth, and the HyperX is significantly better, 1.5x. But even though the HX4 mesh has significantly lower global bandwidth, only 10% instead of 95, it has a higher cost effectiveness per lower bandwidth. So per global bandwidth, sorry. So if we can live with 10%, we get it very cost effective. But that's not what we actually care about in many deep learning workloads. We really care about the all-reduced bandwidth. And the all-reduced bandwidth for all of these networks is more than 90%, because you can just run these rings in various directions. Perfect. And now the cost effectiveness in terms of all-reduced injection bandwidth for the for the HammingMesh is nearly 15 times better than the fat tree. This is a big savings, 15 times. And then the diameter here is less interesting because it doesn't really matter that much for deep learning workloads. So now the question is, can we use this topology that's now nearly 15 times cheaper than a fat tree deployment at the same reduction bandwidth? Well, if we map two one-dimensional decomposed workloads, it's very obvious how to map this to a 2D structure. The third dimension, we would then basically be mapping, like if you have a 4x4x4 job, we would be mapping to different switches, to different board configurations in the physical HX2 mesh. So here we have a 4x4x4, so we first flatten the first dimension here in these two, then we flatten the second dimension in these two, we flatten the second dimension here, and we also flatten out the last one. Perfect. Now the question is, well, the structure is complicated. What happens if things break? So now, if things break, if a single accelerator breaks, we suggest to just fail the whole board, right? Because it's too complicated to deal with those. You can still use the other working accelerators, but not in a parallel configuration. You would be using them on the failed board in a single accelerator configuration. But now let's assume we have this failure pattern here in our deployment. So these are full boards that fail. And the interesting thing is, I can still map a 2x4 job perfectly fine with full bandwidth on this cluster, because each row is fully connected, so I can actually exchange each two rows. On that failed cluster, I can also map a 3x3 job in this way here. So this job will not even realize that there are failed boards in the system from a bandwidth or from a performance perspective. This is quite nice. So we have an extremely high flexibility here just as a view graph. Now, how do we allocate jobs to the system? Well, we just do very simple greedy allocation to map, for example, a job that is a 3x3 job or a 2x3 job. So you see these jobs now come with a geometry, and these geometries, k by n, I can map to this system in a very simple greedy algorithm that I don't want to go into details, but you can look this up in the paper. It's very similar. So what we did is to evaluate the mapping as well as the fault tolerance. We looked at a machine learning as a service workload coming from Alibaba that were running on 6,700 GPUs, and they have a workload trace about the job sizes and the job configurations. So we represent this workload trace as a statistical function, which we are sampling from. You can see this yellow is very much representing the original Alibaba trace. And we now run these sampled workload traces. We map them on our system, on our HammingMesh system. So here are the two configurations, again, the 16x16 HX2 mesh, the 8x8 HX4 mesh, the bigger HX2 mesh, and the bigger HX4 mesh. I don't want to go into too much detail. You need some time to look at these plots, but you can see that if we pull all the tricks that we have, we will get essentially nearly 100% utilization for all of those. So there are various tricks, like you can transpose, you can change the job layout, but they're easy to play with. This is just an ablation study, so we focus here on the nearly 100% allocation. Even if you have random failures, and a very large number of random failures, for example, we have 40 random failures here, which is, for our small cluster, we have only 64 boards total, so 40 out of those fail, but we can still, with all our tricks, nearly allocate 100% of the remaining nodes. This is quite nice, actually. It's quite a fault-tolerant topology. And again, here I would refer you to the paper to look at all the details if you want to learn more. So now, the workload I mentioned that is not super well supported, but actually it is reasonably well supported, is all-to-all. So I want to show just the results for 1,000 nodes all-to-all. We can see that the fat tree nearly gets 100% of the throughput. So this is the upper bound in gigabytes per second for our simulated environment. The 2D HyperX is very close. Dragonfly and tapered fat trees do reasonably well. But then you see that the HX2 mesh is here at 25%, and the HX4 mesh is here at about 10%, as I mentioned before. The 2D torus is unfortunately extremely sad in terms of bandwidth. So we see they still perform reasonably, but what we're really interested in is the all-reduced bandwidth, and what we can see here with the best algorithms, the ring algorithm. So we have let's just ignore the torus all-reduced max bandwidth here. But if you look at the fat tree, of course you can't be better than the fat tree because it's the most expensive, most flexible topology. But this 14 times cheaper, or nearly 15 times cheaper HX4 mesh, and also the HX2 mesh, they are rather competitive. So they nearly achieve 95% of the all-reduced bandwidth that the fat tree gives you. And that's all that matters for your deep learning workload. So great. Now, of course, it's fine. But hey, let's run real workloads. So we designed a set of mini application suite for deep learning jobs. So Shigang Li was doing this in my group, was wonderful. So we looked at many of these jobs like ResNets, BERT, CosmoFlow, DLRM, GPT-2, GPT-3, mixture of experts. So they're all portable MPIC code. So they're literally just generating messages. So they're not full codes to be run, but they're mini applications that emulate the communication pattern that these applications would be doing in practice. It's quite complex, but it's reproducible, so you can just download it here. So if you go to our SPCL GitHub, you'll find DNN CPP proxies there. You find all of the C codes that are runnable as MPI codes in this repository. Here, I don't want to go through all these results. You can look through those results yourself, but the relative cost savings are relatively high. So some of these networks run 8 times more efficient or more cost effective on our topology than on other topologies. So this whole, I'm glad to say that this paper in 2022 actually won the Best Reproducibility Advancement Award at the Supercomputing Conference, which attests its, our strive to make it as reproducible as possible. Here I have to thank Tommaso Bonato, one of my PhD students who was leading the simulation work of this paper and who packaged it up in a wonderful way. Because you can just reproduce all of our work with a simple container. And you will need 0.6 million compute core hours to actually do it, because there are a lot of simulations that we executed. We ran them on SST. More than 120 billion packets have been simulated in our network. But actually, you can totally do it, because what you can do is you can download our Docker container if you have enough compute. You can run your small simulations even on your laptop, and you can run your source code on your run our source code, not your source, on your supercomputer, just with a click of a button. It's very, very simple. I'll show you a video in a couple of minutes. So we're really providing all the scripts to reproduce this work. You can run it locally, as I mentioned, as Python scripts. You can process the generated results. And it's also modular in some sense, that it is easy to modify if you want to evaluate your own topologies in the deep learning setting and compare to HammingMesh. So how do you reproduce our work? You download the Docker container. You just load and run the downloaded container like you would run any other Docker container. It's relatively simple. So here you see it's starting up. So we are getting the root shell in the container. And now you can look at the directory structure in the container, like hxnet subdirectory. And you see various simulation subfolders. Each of the plots in our paper can be reproduced by launching a simulation. You can modify the code of the simulation to run your own network. You will generate communication peers here and then launch these different permutations. And of course, 0.6 million compute hours later, your simulation is done. And we give you also all the plot scripts that generate the plots that we have in the paper. So you can now generate the exact plots in the paper, and that's how you reproduce every single line that we have in the paper itself. So yeah, with that, I would like to close my talk and summarize that we really, if you look at modern deep learning workloads, they are have very specific communication patterns. These resemble a three-dimensional torus, or these can resemble a three-dimensional torus if you tweak the workload enough. You can now co-design an AI supercomputer, a global system AI supercomputer with the HammingMesh topology to be a kind of a two-dimensional representation of it and map these three-dimensional workloads, or sometimes even one and two-dimensional workloads, to this system topology at a very high utilization. You can get a cost benefit of up to 14.5 times at 16,000 nodes, and even the all-to-all gets significantly cheaper, which is very nice. And then for real topologies, you can get for real training of real networks, you can get a 7.8 times, up to 7.8 times performance benefit. So reproducibility goes beyond this paper. You can actually use our mini proxies to build your own, to evaluate your own communication relationships, and we spend a whole lot of time to make it fully reproducible. We got the 3 badges, and also happily got the Reproducibility Advancement Award. So yeah, thank you very much, and